Hi guys, we're just proving this little theorem here, actually very important because it helps us in problems when we need to figure out the spectrum of certain operators, at least when those operators act on Hilbert spaces. So it's important because it clearly exploits the symmetry of the operators. If you have a normal operator, a unitary operator, or a self-adjoint one, then certain things are well given from the start. You don't have to investigate them any further. For instance, the residual spectrum in all three cases would be empty. Then if you're dealing with a unitary operator, then the spectrum has to be, well, subset of this either boundary of the unit disk or +1, -1. And if you're in the self-adjoint case, then the whole spectrum is real. We have proven everything at this point except for this little red piece here, that the spectrum of a self-adjoint operator is completely real. So to get started with that, let's do a computation that you have seen for sure multiple times. For 3, we begin with showing that all the eigenvalues are real. All right, we begin with showing that the point spectrum is real. This is super easy. So if Tx is equal to lambda x with x non-zero, then, so lambda x comma x, now you can choose freely where you want to put in the lambda. Let's put it into the first vector. Then I have lambda x x, but you have the eigenvector equation, so it would give you a Tx comma x. Now you use the adjoint, so move it to the other one. You have x t star x, but since the guy is self-adjoint, the star actually goes out. You got x tx, and now you do the same eigenvector equation. Maybe here you would have x lambda x, and then you pull it out, but now it comes out with a complex conjugate in general, right? So you get lambda bar x comma x. All right, since the x is a non-zero vector, that inner product x with x, which is just its norm squared, is different from 0. You can divide it out from the whole equation, and then what you have there is that lambda is equal to its complex conjugate, and that's precisely the statement that lambda is real. Okay, good. So lambda equals lambda bar, meaning lambda is real. Okay, so that shows that the point spectrum is certainly real, showing sigma point spectrum is real. All right, but we need more now. Okay, good. So what next? In turn, for lambda non-real, this then means that, well, this guy is always injective because all the eigenvalues are real, right? So if lambda is a non-real scalar, then the kernel always has to be trivial, and so range lambda I minus t is dense in H by the projection lemma. All right, so we used this argument in the first part of this proof, showing that the residual spectrum is empty. Okay, is dense for the same, is dense in H for lambda not real by the projection lemma. All right, now moving ahead, let's do a little side computation additionally with arbitrary AB real and x a vector. So what I'm going to compute now is here the following thing. So a plus ib, this would correspond to the lambda, and then identity minus t, all of that acting on x squared. And since you're in a Hilbert space, this norm squared is inner product, same quantity with itself. You use that fact, and then again you just pull that trick with the adjoint. You move things to the other vector, but then if you do this, you have to remember that taking the adjoint is a conjugate linear operation. So that's why here, when you have it in the second vector, this plus here changes to a minus because you got give a complex conjugate bar. The identity stays the same because it's self-adjoint, and also t stays the same because t is self-adjoint, right? We're currently doing this direction. And then the other part is still there, a plus I bi minus t, and then x, like so. All right, let's move this a little bit here. So this is pure algebra, just exploiting the definition of the adjoint and using the fact that you have a self-adjoint operator. And now you can simplify this piece a little bit. Should check for yourself. This is just ai minus tx, so a would be the real part of lambda, and then norm squared plus b squared x squared, right? So in particular, if you drop a non-negative term, this guy tells you that, well, why don't we write it with lambda instead of ab? Lambda I minus tx is at least, I gotta take square root, so imaginary part lambda, absolute value of x. Okay, that's precisely what we just showed. All right, good. This implies, I claim, that range of lambda I minus t is closed for lambda non-real. So when the imaginary part is strictly positive, right? Why is this? Indeed, usual trick, take a sequence which is convergent and show that its limit is in the same set. So let's take a sequence in the range of lambda I minus t, okay, is convergent. Say yn as n goes to infinity goes to y. Then, because it's a sequence in the range, for some xn, we have that yn is lambda I minus txn, right? Because it's a sequence in the range, so n natural number. Okay, good. Consequently, using now this little helper, because this is valid for any point in the vector space. So I have then, so the left-hand side, this is lambda I minus txn, this is just yn, says is at least as big as imaginary part of lambda and then xn, right? So yeah, but this clearly shows that the sequence of the xn's has to be a Cauchy sequence, right? Because you could have done this here with the difference, yn minus ym, xn minus xm, and this quantity, that's important. This is different from 0 because you're away from the real axis, right? Yeah, but since this guy here is Cauchy, that we started with a convergent sequence, so that one is particular Cauchy, then this guy here has to be Cauchy. That's what I just said, right? So this says that xn, sequence in a Hilbert space, is Cauchy, so convergent. So convergent. Xn, say, goes to x. Okay. Hence, let's now complete it. Hence, by continuity of t after all is bounded linear operators, in particular continuous. This was like the first result in this module. Yn lambda I minus txn, well, xn goes to x, so then this guy will go to lambda I minus tx. And that, of course, is a quantity. And remember, yn went to y on the left, so then I have here y is equal to lambda I tx, and that is in the range of lambda I minus t. So indeed, the range is closed, right? This was the goal. I have this convergent sequence up here, yn goes to y, and I have to show that the limit is again in the range, and that's what I've just done with here. Okay, good. So that's we know now the range is closed. Altogether, range is closed. Yeah, but we already know that for the non-real eigenvalues lambda, we already have this one, right? This comes from the projection lemma, because if you are off the real axis, the kernel is always the zero vector space. So the projection lemma, which has two pieces up front, that kernel, and then the closure of the range, the kernel is now zero because I'm away from the real line, right? For all lambda non-real. But what I just showed is that the range is actually closed. That's why now you can erase that bar here on top, and then what it tells you is that the guy is surjective, right? So we have now both. You have for non-real lambda, you have it's both injective and surjective, so it's bijective, and now you use the inverse mapping theorem, so it's invertible for all non-real lambda, and that means all non-real lambda are in the resolvent, right? And then we're done, right? For all this, thus lambda I minus t is invertible for all lambda non-real, inverse mapping theorem, right? And because I showed with this argument the bijectivity, right? And then we use the inverse mapping theorem to get the boundedness of the inverse. Invertible for all non-real lambda, and so the spectrum must be a subset of the real line. Okay, this completes the proof. Okay, excellent, excellent. All right, so this closes now, in fact, the section on the spectrum for now. Now we will study a special class of operators where the spectrum will come back a lot. And of course, in the exercises, there will be lots of problem of, hey, here's a space, here's an operator, figure out what's the spectrum, the resolvent, and all these parts. Okay. All right, so let's go ahead. So now the next section, this is actually the last one, but at least for me, the most important one. Because it really blends almost everything together in a nice theory. And it is, for me, the most important one, because if you think back to linear algebra, so in the usually in the last part of the semester, after one has, you know, assembled all the basic notions, very much like here, we learned about Banach spaces, Hilbert spaces, and now we do the spectrum, and now we have some big theorems. And the same happens in linear algebra, because there probably one of the biggest theorems are the spectral theorems, so diagonalizability of, let's just say, matrices, right? So given a particular matrix, can you bring it in some special form called normal form? And then, well, big theorem is if you have a Hermitian matrix, then that guy has, well, eigenvalues. Sure, any matrix has n eigenvalues if the scalar field is the complex number field, and if the matrix is n by n. But now, if you're in the Hermitian case, the theorem says that, well, then there's enough eigenvectors to have a basis for your vector space. And so you can diagonalize the guy. And now in this section, we will have very much an analog of this spectral theorem. So there will be a special class of operators. These are the compact operators. And for these guys, we will prove, well, they have plenty of eigenvalues and associated eigenvectors, so that we can, well, diagonalize them in whatever sense that is. All right, it will all be clear. And these special types of operators are the so-called compact operators. Right, so definition, so that the name already now indicates compactness here. So at this point, it's a good idea to review notions of compactness from the metric space module. So we will need the compactness, where, well, every open cover has a finite subcover. We will need the sequential compactness, so sequences have convergent subsequences, and the limit is again in the set that you're studying. And then there's the totally boundedness, so you can cover the thing with finitely many disks of arbitrary small radius. So some people call totally bounded pre-compact, but I prefer totally bounded. Right? So we will have to juggle these three notions here quite simultaneously all the time. So if you don't recall them anymore, please review at this moment. There is in the introductory chapter of the lecture notes, they're summarized. Okay, they're kind of equivalent if you're working in complete metric spaces. All right. So let's get started. Enough said. So let XX and YY be Banach spaces. We will be at least here in the Banach space world. You can do this a bit more general. You can do it over normed linear spaces, but then you have to be very careful with your statements, because completeness is not guaranteed. So here's a notion, COM XY, so COM for compact and XY. This will be the compact linear transformations is the set of bounded linear transformations. I like to build this in the theory, some into the definition. Some people don't do it, they just work with the following line. That line actually implies the boundedness. So what I build in definition, so that this set, so this is the image of the unit ball in X space, and then you throw in all the limit points, that this thing is compact in Y. So this is a subset of Y, and the distinguishing feature of a compact linear transformation is that this guy is compact in Y. All right. Here, B10, let's just remind you of this. This is the open unit ball in X space. Okay. And we write, in case you're working with operators, so X, capital X is equal to Y, then I just will write com X for com X comma X. Okay, so let's think about this a little bit. So T being a bounded operator, it's gonna map a bounded set to something bounded. All right, so T, in other words, T B10 is always going to be bounded, right? But then, since the definition involves the closure, that thing is going to be a bounded enclosed set. Now, if you were in finite dimensions, then this would be compact, of course, right? This is part of the equivalent norm theorem. The dimension of a vector space, of a normed linear vector space, is finite if and only if every bounded enclosed subset is compact, right? But here we are in general infinite dimensions, so it is not guaranteed at all that this yellow guy should be compact. If it is, then you're dealing with a compact linear transformation, right? So that is the distinguished special feature of compact linear transformations. Okay, good. I already said, if you're in finite dimensions, well, in finite dimensions everything is boring, because if you have a linear map between finite dimensional spaces, that thing is bounded. That we discovered in the very first week, and what I just said is that thing would also be compact. So in linear algebra, there's no need to study compact linear transformations because everything is compact, right? But here in infinite dimensions, that's just not the case, and we will see soon enough, not every bounded linear transformation is compact, right? So further emphasizing that really having a compact linear transformation is a special thing. Okay, good. All right, so moving ahead, definition, the finite rank linear transformations. We say a linear transformation T LXY from one Banach space to another is of finite rank. Well, if the dimension of the range, right, the range is a subspace, so a vector space in its own right, and if that thing has a finite dimension, as defined in linear algebra, then you call this guy a finite rank linear transformation. Okay, good. These are two definitions. It should be clear already now by what I said earlier that if you have a finite rank linear transformation, then you have a compact linear transformation, right? Because then this here, this guy here, this would be a closed and bounded subset of a finite dimensional space, right? Because this green bubble is contained in the range, and if your range is finite dimensional, then you have a closed bounded subset in a finite dimensional space, hence it is compact. Right. We will summarize this later in the first theorem. For now, we will need a equivalent characterization of a compact linear transformations besides this definition. It will be useful to have a sequence criterion, but it shouldn't come as a surprise because of the thing that I said at the very beginning. Compactness is equivalent to sequential compactness. So meaning if you have certain sequences, they have convergent subsequences. So that's why probably the following thing is not such a surprise. If you have two Banach spaces, X and Y, then a T in LXY is compact if and only if for every bounded sequence Xn, the image sequence Txn, and one finishes this sequence in Y, has a subsequence. The subsequence convergent in Y. Okay, that's the thing. And we will alternatively switch between these two things. So sometimes in proving that something is compact, we will use the original definition, and sometimes we will use this proposition, right? Because they are equivalent. Some people actually define compact operators with the help of this proposition, right? So that the thing is compact by definition if for every bounded sequence the image sequence has a subsequence that is convergent in the space Y. Okay. Proof. Well, this is juggling with the different notions of compactness. So by linearity of T and completeness of Y, we see that T is compact if and only if T maps bounded sets in X to totally bounded ones in Y. Right, so why is this? Well, the linearity allows me, this is by the way a property that we used when we proved the open mapping theorem. We used the scaling invariance. So if you have TBR0 and the closure, then you can move out the R here and live with the radius 1, right? So that's what I mean by the scaling invariance. So if this image of the closure of the image of the unit ball is compact, then you would have this actually for any ball of arbitrary radius, right? And that's why here, if you have bounded sets, then they're certainly sitting inside a ball of arbitrary large radius. And that's why this first implication is true there. T maps bounded sets in X to totally bounded ones in Y. Up front, by the definition, it maps it to compact ones, but the compactness and totally boundedness in a complete metric space are exactly the same thing. Right? So that's why I can write this. Okay, but now moving ahead, now I jump to sequential compactness, but a set M in a Banach space is totally bounded, if and only if every sequence in M has a convergent subsequence with limit in M, right? Because the total boundedness and the sequential compactness in complete metric spaces are also the same thing. Okay, and that's it. So that is this one here. All right, so now I already said up front, so compact linear transformations are of course bounded linear transformations, special types, and we will see soon enough that actually, well, let's write it down. We will see soon that COMXY is actually a proper subset of the bounded linear transformation. So not, in other words, not every bounded linear transformation is compact, right? For generic x and y. Okay, good. So, but before we get there, we first need a handful of properties. Maybe I will just be able to summarize them now, and then we will have to prove them next time. That will take quite a while. It's very much like this theorem once we had defined the adjoint, so there's lots of properties to be done, to be proven. So you have 3 Banach spaces. Then here are the following properties. The first one I already argued or said earlier why this is true. If you have something of finite rank, then it is compact. COMXY. More interestingly, COMXY is a norm-closed subspace. Of LXY. So that means if you have a sequence of compact linear transformations and that sequence is convergent, then this second property says that the limit will be again a compact linear transformation. So in particular, if you combine 1 and 2, if you have a sequence of finite rank linear transformations and that sequence is convergent, then its limit will be compact. And that is very useful. The next one, 3 and 4, these are algebraic properties. If you have taken some class in abstract algebra, then these statements say that the compact operators form a two-sided ideal in, well, the LXY, right? So in other words, if you have compact S here, and you compose it with something bounded from the right, then the composition will be compact. And you can do this also from the left. That's why two-sided ideal. So if you have compact S and bounded linear YZ, then the other way around, TS is also compact in XZ. Okay, this is also very useful. And then the last one, sometimes this is a theorem stated by itself. I will include it here on the properties. T is compact if and only if its dual is compact. So dual goes from the dual spaces, but in reversed order. This is called Schauder's theorem, this fifth part only, right? So the name Schauder we will encounter again in this section later on. All right, so these are the basic properties of compact linear transformations, and we will prove them next time. Once we have this, then we will start discussing examples and then building up gradually more theory about these compact guys. All right, I hope I'll see you soon.